I would like to welcome back our speaker, Dr. Brad Davis. Dr. Davis is an associate professor of civil engineering at the University of Kentucky, and he is owner of Davis Structural Engineering. He provides consulting services for structural vibration, steel connections, and advanced steel design applications. He is licensed in approximately a dozen states. Dr. Davis is a member of the AISC Committee on Manuals and Textbooks and a consultant for the Steel Solutions Center. He has published approximately 24 journal and conference papers on vibration and has presented a number of continuing education courses for vibrations and steel connections. Brad, thanks for being here, and I'll now hand it off to you.
Well, thank you very much, Nate, and thank you all for attending our webinar session this afternoon. This is session 4, Bracing Connections. You can see from our schedule that this is the last session. We've been covering moment connections, and now we're switching to bracing connections. So in this session, we'll be learning how to design connections such as these. Our topics, we're going to start with basic bracing connections, just pretty simple ones, where we have just a gusset plate and brace connected to a member, either a column or a beam. So these are simple. We'll use these to introduce some limit states that are not new, but new to us perhaps during this webinar series. And we will be working some example calculations in this section. We'll spend most of our time, though, on the heavy bracing connections, probably more properly termed corner connections, and as you would see in braced frames. There's a lot to be said about the internal force distribution for these kinds of connections, so we will spend some time on that. These are very highly statically indeterminate, and it's really a pretty interesting problem, so we will spend some time there. We have various limit states. Some of them new to us, some of them not, most of them not actually. So we'll spend time there. And finally, we'll do some example calculations. By basic and heavy bracing connections, I'm referring to these. And these are not technical terms. These are just terms I'm using to describe one versus the other. In these basic connections, we have something like you see on the left, where we have the brace coming in, probably on some diagonal, maybe not though, and it's connected to the column, or it could be a beam, with just a simple element such as a gusset plate shown in this connection, although there's a couple different ways of doing this, probably more than a couple. This is a very common way shown. By heavy bracing connections, I'm referring to connections such as this one, in which we have the brace coming into the corner that's made by a beam and a column. And usually what happens is that the geometry is such that we have a gusset plate that's connected to both the beam and the column, and we can have some pretty enormous loads in these connections. So we need to be able to design the brace to gusset connection, and then the gusset to column connection, and gusset to beam connection. And we got to really be careful not to forget this connection up here between the beam and the column, because that can really get hammered. So we'll be speaking about that a little bit as we go along. So these basic bracing connections, there's various ways of making such connections. I'm showing two here. The one on the left, as I mentioned before, we have the brace, and then we have some simple elements such as this plate that we're using to connect that to the member, the column in this case. This is probably the most common way of doing this. If we have an HSS brace, we will most likely slot that brace, fit it over the gusset plate, and have one erection bolt, and then field weld the HSS. So that's one of the other common things that happens there. On the right, we see a little bit more of an unusual connection. In this one, the way it's shown, we have this T, and this can be a built-up T or a T cut from a WT or a W shape. And that T is, the stem of that T is shop welded to the brace, and then this flange of the T gets bolted to the column, or it could be a beam if this picture turns 90 degrees. This connection, as far as today's talk goes, the main motivation here is that this is a simple connection that lets us talk about the prying action and some other interesting limit states, mainly over here. That's our primary motivation for including it. All right, let's take a look at this simple one where we have the plate that's welded to the column flange. The limit states for this connection, let's start at the brace side and trace the limit states over to the member side using our approach that we've described previously. Well, starting in the angle, we have angle tensile yielding in the gross section. Moving to this first row of bolts, we have angle tensile rupture on the effective net section, or the effective net area, and we have shear lag most likely happening here. Definitely do with this case, and we often are going to have that. We have block shear. We have this little pattern coming out there, block shear. Then we move to shear transfer to get the load into the plate. Shear transfer is our combined limit state that considers the bolt shear rupture strength and the bearing and tear out strength of both connected parts. We would calculate the effective fastener strength at each of the three fasteners, sum those to get phi Tn in this case to compare to T sub U. Now moving into the plate, we have tensile yielding, tensile rupture, or compressive yielding or buckling on what's called the Whitmore section. Notice that Whitmore section in all three of these. And we'll discuss that in some detail shortly. Note that the way this is drawn, this brace is in tension, so tensile yielding and rupture would apply. If this brace force was reversed into compression, then the compressive yielding or buckling down here would apply. We could have block shear. As a limit state, we would check if we have more than one row of bolts. Finally, we have the base metal strength down here at the weld. Also, just have written them out, but just naming the other limit states, we have weld rupture, and then we also have whatever column limit states apply. In this case, presumably this plate is centered on the web, so we would have web local yielding applying whether this brace force is in tension or compression, or we'd have web local crippling if this brace force is in compression, causing a compressive stress field in this region. If we had an HSS column, then we have punching shear and web or wall plastification or bending out of plane as well. Now, the Whitmore section, I mentioned that, so let's talk in some detail about what that's all about. We go to the manual figure 9-1 for help on this, and here's the idea. Let's consider this connection plate at the top here. In this plate, we have 3 bolts at some spacing, and we have some applied tension or compressive load. This plate can be pretty large transverse to the load, and just intuitively, we would expect the region kind of in this region over here to be where the high stresses would be. And if you get far enough away, either this way or down the other way, these regions of the plate don't even know anything is happening. So we need some way to define our critical section in this region in the middle where the high stresses are. And the Whitmore section is how we do this. If you go in the manual, you'll see pictures sort of like this one, and you'll see over the length of the connection, we spread the load at 30 degrees, as shown. And wherever that and at the location where it intersects at the back of the connection, like here, that defines our critical section. And we can calculate the gross area for a tensile yielding check, net area for tensile rupture check, or I guess gross area also for the compression check. This is going to be our critical section. Now, oftentimes the plate's not very wide, so this 30-degree spread runs off the edge of the plate. In that case, the critical section is, of course, just the plate width, or the plate width times the thickness. And we would just simply say the Whitmore section doesn't control in this case. We can also use the Whitmore section concept to define the effective weld length. In many of these connections, we're going to have to use some significant engineering judgment when we get to the weld check. We can have the weld concentric with the plate as we and load as we see here, or sometimes not. So we need some tools just to help us out. One thing we can use to help with our engineering judgment is to use this Whitmore section spread to come out and see how long of an area to use, or long of a length of weld to use. Again, this is just engineering judgment. The idea is that the weld up here may not be helping us very much, so let's ignore it, which will be conservative. Plate compression, mentioned that briefly. So let's talk about that for a little bit here. Say we have a case like shown on the right, the brace is in compression. So we have yielding or buckling in this region of the plate over here. We evaluate this region for compression using the spec, section J4.4, and you see our acceptance criterion right here. Our piece of view can't exceed VPN using LRFD. VPN is calculated as shown here. If our unbraced length divided by the radius of gyration does not exceed 25, then we just calculate the yielding strength in this region. If the unbraced length over R exceeds 25, we have to calculate the flexural buckling strength per section E3. Now, the unbraced length L sub C is just K times L, and that is not as easy to define as what it might sound. So we go into Design Guide 29, our vertical bracing connections design guide that has a tremendous number of examples, and see what they're using in there for the various K values. A lot of times it's 0.5, sometimes it's 1.2. So we go in there and figure out what to use for K and L. The weld rupture design strength, we check this the same way we usually do, in which we have this equation from the spec, equation J2-3. Our F sub NW is just the ultimate shear stress of the weld material times this directional factor. And the idea here is that the weld is stronger. The load is not parallel to the weld, is at some angle to the weld. And this data is measured between the weld longitudinal axis and the load angle. We're usually going to use our shortcut equation from the manual, equation 8-1 on page 8-8, and it goes like this. Using LRFD, it's 1.392. That's kips per 16th size per inch of length. D is the number of 16ths. L is the length of weld. Of course, in here, it'd be both, add the two on the near side and far side. And then the directional factor. The only trick here will be that sometimes we need to use some judgment in defining the length. So let's look at just a quick little example. In this case, we have 70 KSI, so we can use our shortcut equation. And we have this arrangement where it's not super convenient because the weld is not, the entire weld group from all the way to the top, from the top of the plate to the bottom of the plate is not concentric with T sub U. And the T sub U is at 41.6 degree angle. Now, the way we're just going to have to use engineering judgment to deal with this. One approach would be to use the weld from the bottom up to some height, maybe even the very top of this, if that's what our engineering judgment tells us is okay. And we have some eccentricity. We have some moment on this because the the load is not going through the center of the weld group. So we have some eccentricity. Go to Part 8 of the manual to the eccentrically loaded weld group tables and calculate the strength. Another option is to define the effective weld length that is concentric with T sub U. And one approach could be this. You could start at this side of the connection, spread the load at 30 degrees like a Whitmore spread, and see where that puts these lines intersecting the column. This one's intersecting up here. This one's off the bottom of the plate. And then consider that I will only want to consider the amount of weld that's concentric in here with T sub U. And just grab that length and call that the effective weld length, and then ignore the eccentricity. The idea there is you can't make the connection weaker by adding weld up here. Using this approach, in this problem, the length of weld ends up being 8.4 inches. And to calculate our strength, come down here, use our shortcut equation. We have 4/16 for the weld size. This length 8.4, I've knocked off a 1/4 inch. And again, that's just engineering judgment. I don't think that's written in the spec or manual anywhere. I'm knocking off a 1/4 inch because down here at the bottom of this, the plate's coming in at a sharp angle, and maybe right near the end of that weld, you're not getting the full size of the weld built out. So I'm knocking off a 1 weld size. We have weld near side and far side, so we have 2. And then have our directional factor. Notice the 41.6 degrees is the angle between the load and the weld. For this arrangement, this comes out to be 115 kips. We would evaluate the weld by comparing that to T sub U to see if it's okay or not. All right, let's talk about these connections in which we have a instead of having just a plate that's welded to the column. In this case, for whatever reason, we want to use this T-shaped connecting element. This can be either the stem of the T, can be built up, or it can be a plate that's welded to the flange of the T, or this can be cut from a T. It doesn't matter. Just this is for illustration mostly. And in this connection, this connected part is welded in the shop to the brace, and then the flange is bolted to the column in the field. Let's go through the limit states for the connection that's arranged as shown here. First, starting on the angle side, we have angle tensile yielding on the gross area. We always start with that one because it's very easy. It serves as a nice warm-up. We do note that that's really a member design limit state, but we might as well start with that. Next, moving into the first real connection design limit state will be tensile rupture through a section approximately here. Now, the net area is the same as the gross area in this case, but because only the vertical legs are connected, we have shear lag. So we need to go into Part D of the manual, Table D 3.1, and get the shear lag factor out of there and use that to calculate the tensile rupture strength of the angles depending on whether this is a single or double angle brace. We have base metal strength at the welds, and that's mostly along this toe of this angle. We want to make sure that we don't have a shear rupture along this line at the weld. Next, moving from the angle, we need to get the load into the stem. So we have the angle to stem weld, and in this case, I'm drawing a double-sided fillet weld. So I have a weld along this line and then another one over here. The weld rupture there. Now moving into the T-stem, we have several limit states there. We have this Whitmore section consideration. So we define this, we have this 30-degree spread over the length of the weld. This goes from over the length of the weld probably wouldn't be as long as shown in this picture. Have this 30 degree spread, and at the back of this connection, that's going to define a critical section. And that critical section is used to check tensile yielding, tensile rupture, that's if the brace is in tension as shown here, or compression if on this Whitmore section, if this load is reversed and the brace is in compression, we'll have compressive yielding or buckling in this region. And the unbraced length would be from about here to here. And then, of course, we need to look up the K, see what we need to use for K. We also have block shear, pattern like this U-shaped pattern like shown there. Have block shear of the stem. Seems like we could also have block shear along the L-shaped pattern that went down like so and over this way. So you just got to use your engineering judgment to define these patterns and check whichever ones you think are reasonable and believable. Another limit state to check would be shear yielding. This T sub U has a vertical component, and so we need to check shear yielding along the line about like this. And of course, where exactly you put that left to right depends on the geometry. You need to come up with the worst case, smallest gross area subject to shear, obviously. Now that's the T stem. Now we need to move into the T flange. Here we have several things going on. The most exciting thing here is that we have the horizontal component of T sub U, this T sub U times this theta, shown in plan view looks like this. Here's a plan view showing the T stem on the right and T flange on the left. And because of this arrangement, the T flange can bend out of plane. If it bends out of plane, and this was, we talked about this a lot back in session 2, we can have if this flange can bend enough, then we'll have a fulcrum develop at the corners, like one at this corner at the top of the picture, and the other one down here at the bottom. And that will cause prying forces, which will increase the forces on the bolts, and we must take those into account. Now, the preferred approach is to make this flange thick enough so that the prying forces don't develop. To evaluate this stuff, we go into the manual, part 9, starting on about page 9-10. And there's procedures in there, and we will go through some of those today. We also have shear yielding. That would be, in this plan view, shear yielding through a section about like this, and of course down here as well. And shown in this elevation view, we have the shear yielding along a line about like this, and then on the other side of the stem also. We have shear rupture through these bolts, through all these bolts shown in this elevation of the T flange. We have block shear as well. We have an L-shaped pattern where we have like the pattern goes like this, pulls out this piece over here. This part block shears out, and of course this piece over here does too. So we have these basic mundane limit states. Also, we have the more exciting one like the flange bending and prying action, but then we have these that we're just taking all the time, all over the place in connection design. And we've seen those several times, so they'll be de-emphasized today. More limit states. We've gotten the load through the angle, weld, stem, bolts, flange of the T, and flange of the, well, I guess we've gotten 2 here. We've gotten 2 of these bolts, and these bolts are in combined tension and shear. The vertical component of T sub U causes shear on these bolts. The horizontal component of TU causes tension on the bolts. And that could be with prying action added to that, by the way, if we haven't made our T flange and column flange thick enough. So we have combined tension and shear. We also have shear transfer. That's our combined bolt rupture, bearing, and tear out check. We could have slip resistance. That's important to us along this plane. That's if the engineer of record has decided to make this an SC connection, a slip critical connection. Now that we have the load through the bolts, now we're into the column flange. And the first thing we need to do is check the column flange for out-of-plane bending and prying action, just like we did the T flange on the previous slide, or talked about it. So we need to make sure the flange is thick enough to prevent prying action, or else we need to take the prying action into account in our bolt design. We had the load through the flange now. Now to the column web. Regardless of whether this brace is in tension or compression, we have web local yielding in this region behind these bolts. If this brace is in compression, then we have web local crippling in this region. So let's do a quick example. I'm just going to, mostly today we're looking at selected limit states. Just the ones that are not super duper obvious, that we just don't have time to go through all of them. We'd be here until tomorrow trying to get through all the limit states for some of these connections. In this little example, I want to evaluate slip resistance of the connection shown on the right. We have a T sub U of 150 kips. Our angle theta is 50 degrees. We have 3/4 inch diameter grade A325 SC bolts. So we'll get a chance to illustrate this SC, or the slip resistance calculation. We have a Class B fading surface between these two flanges. And we have oversized holes in the T stem, or T flange. To calculate the strength for this limit state, or really it's not strength, it's the slip resistance, we need to go use the spec equations J3-4 and 3-5A. And this equation is our basic slip resistance equation or expression, except for this case of SC that's added. And this factor accounts for the fact that there's a component of the applied force that's trying to pull these plies apart. That's reducing the normal force and thus reducing the friction. So it's going to reduce the slip resistance. So we have this factor added in. We're noting that this equation in the spec is per bolt. The per bolt equation. Our phi for this connection is 0.85. Slip resistance is it's either unique or nearly unique limit state in that phi varies depending on the situation. If you have oversized holes, phi is 0.85. The mean slip coefficient for Class B is 0.5. The bolt, let's jump down here to the bolt minimum pretension. This is from table J3.1. The minimum pretension is 28 kips. For our calculations, we're going to want the average bolt pretension, and that's about 13% more, roughly. So we have this factor D sub U that's always 1.13 in the specification. That's just to take convert this min to an average. We have HF as the factor for fillers, and that's 1 if we have no fillers, which we can assume we're slapping this T flange right up against the column flange, so we don't really have any fillers in there. If we had 1 filler jammed in there, it'd still be 1. We'd still have 1 there. If we had multiple fillers stacked on top of each other, or beside of each other in this case, then we'd have a lower value for H sub F. Number of slip planes is just 1. Just 1 slip plane along there. Going to our equation or case of SC, it's 1 minus this applied force that's pulling the connection apart. For our example, is T sub U times the sine of theta, divided by the clamping force. And this, again, this is the minimum pretension times the ratio of the average to min. So these two are the average pretension per bolt times the number of bolts. Plugging all these numbers into our equation, we get 0.697. So we have about a 30% reduction in the slip resistance due to this force that's pulling the plies apart. Keeping on through the calculations, we get to our equation for the strength, or slip resistance. Got the phi going in there, slip coefficient going in there, and all these other values coming in here. we get 9.37 kips per bolt. Not much. We sum those up. We have 12 bolts. You can see we have 6 rows there, and we have 2 columns of bolts. We have 12. Multiply this out, we have 112 kips. That's our slip resistance, our design slip resistance. Required force there will be T sub u times cosine theta, and that's 96.4 kips. That does not exceed 112 kips, so we're okay. So this limit state is okay. Let's also check these bolts for combined tension and shear. So I want to check the bolt design strength for combined shear and tension. Note that even though this is an SC connection, we have to check it as if it's a bearing connection also. We always have to do that. We have a sort of a 2-part criterion for combined shear and tension. First, we check shear, and here's our main criterion for that. It's just R sub u can't exceed phi Rn. Phi Rn for bolt rupture is just this: phi times FNV times area of the bolt. Now I can divide through by the area of the bolt and get this in terms of stresses. So R sub u divided by the area of the bolt, that's F sub u V. That's just the stress. That's KSI in the bolt due to shear. And say that needs to be less than or equal to F phi times F sub NV. And that's the way it's written in this section on these SC connections. It says the available shear stress of the fastener shall equal or exceed the required shear stress F sub RV generic or F sub UV for LRFD. That's near the end of section J 3.7. Also, we need to check the bolts for tension in the presence of shear. If you have enough shear on the bolt, that's going to reduce its strength in tension. So it's tension in the presence of shear. Our criterion for this is R sub u can't exceed phi Rn, and I lost the phi there. Phi Rn is phi times F sub nt primed times the area of the bolt. Now F sub nt primed comes from our interaction curve. We have shear on the x, tension on the y. F sub nt primed is this. This first expression is this sloping line, and of course, this can never go above just phi times FNT. So I have this less than or equal to over here on the right. Let's continue this calculation. The shear stress, the shear overall is this vertical component of the brace force is 150 kips times the cosine of 50 degrees. Divide that by the number of bolts in the bolt area. And this comes out to 18.2 KSI in each of the bolts. We evaluate the bolts at this step by comparing that to phi times FNV, which is 40.5 KSI. So far, this is okay. Now, we'll say bearing takeout need to be considered also. Really, we should probably be doing an overall shear transfer check here. All right, moving down to tension in the presence of shear. We calculate our FNT primed, plugging our numbers in. Here's our F sub UV going in. And we get 76.6 KSI from this expression. Now, whatever we get from that, we can never exceed F sub NT, 90 KSI. And you see that we don't. If we would have gotten 92 out of this, then we stop and use 90. All right, now calculating the strength, we have phi 0.75 times 76.6 KSI times the area of one bolt, or 25.4 kips per bolt. That's the strength of one of these bolts in tension if it's subjected to the shear that we have. We can calculate what we have in the bolts as far as the required strength, and that's going to be the required tensile strength of the bolt. and that's 150 kips times the sine of 50 degrees. This is the horizontal component of the brace force. Divide that by 12, and you get the per bolt. So we have 9.58 kips per bolt. That does not exceed the available or design strength, 25.4 kips. So this limit states okay here as well. It's okay at a shear step and then at the tension in the presence of shear step. So it's okay overall. So these bolts are okay for combined shear and tension. Just a few more comments. We have lots of other more mundane basic limit states that we didn't really check, especially the T flange. We need to check shear yielding. That'll be along a line like through here, and of course on the other side of the stem as well. Shear rupture through these bolt holes. Block shear transfer between the T flange and the column flange. And finally, the flange bending, of this T flange, and of course the column flange as well. So there's lots of stuff we did not show here. Not trying to show complete examples, just trying to show some selected limit states. Now let's move into heavy bracing connections. Probably more properly termed corner connections. Now, in the left-hand one is a pretty typical looking one. Here we have a pretty good sized beam, W21 by 83, a column, W14, and there's a couple of heavy angles, like a heavy double angle that has a pretty large load in this case. This angle is connected to gusset plate by bolts in the field. This gusset plate is connected to an end plate and the beam in the shop. And this end plate is also connected to the beam in the shop. And then, of course, this end plate bolts to the column in the field. And I guess the brace then bolts to the gusset plate in the field. On the right, we see a connection that's a little different in that we have a W shape for the brace. So we need some way to connect the flanges and the web to the gusset plate. And we use what are called claw angles in this picture. There's 4 angles total at these flanges to connect the brace flange to the gusset plate. Also, we have this web plate in the middle. So we are connecting all of the parts of this brace to the gusset plate. Of course, we have connection to the beam, between the gusset plate to the beam and the gusset plate to the column. Beam to the column. It's easy to forget that guy, but it's a major player. A few comments first. The gusset plate is usually welded to the beam. Is shop welded there. It's usually bolted to the column. Now, there's about at least 3 different ways that this happens. First, we can have an end plate like shown in this picture. The end plate welded to the end of the beam and this gusset plate. We can have a single plate, I've seen them called shear plates. It looks like a single plate shear connection welded to the column and then bolted to the gusset plate. It's not a single plate shear connection, but it looks like one. We can also have double angles there. Note one thing: the forces at the beam and the column are indeterminate, so we need some way to determine what load goes where. How much of this 840 goes through this connection and how much goes through this connection. We have a recommended method called the Uniform Force Method in the manual Part 13 and in Design Guide 29. Let's talk about these internal force distributions for a little while. This is really the star of the show for bracing connections. First, let's start with the easy ones, the brace to gusset plate forces. And I'm illustrating this with the claw angles because that's the most difficult one. We have this brace force P sub U, and we need to know how much of that goes through these web plates, and of course the rest of it goes through the claw angles. And we need to use engineering judgment for this, and my judgment is that this is the way to do it. Take the area of the web, H times TW, divided by the area of the brace, that ratio, and just take that amount of P sub U and put that through these web plates. Everything else goes through the claw angles, so it's just everything. Note that the fillet area in the brace is going to end up with the flanges in this kind of approach. Now, moving to the internal force distribution for the gusset plate, here's where it gets really exciting. Looking at the left, we have the external forces. You can see we have the brace force. It's at some angle theta. It's always measured from the vertical in part 13 of the manual. We have lots of forces here. We have the column axial load. We have a force transferring in from the adjacent bay. We have the axial load in the beam and the reaction, just a shear reaction in the beam. Looking at the gusset plate, here's where we draw the first of our free body diagrams, and we have lots of free body diagrams that we need to be drawing and thinking while we're doing these connections so we don't screw up. If you look at the gusset plate, it's subjected to the load P, which has a horizontal component H, vertical component V. At the column side, we have a horizontal force connecting this to the column, H sub C, and a vertical force connecting this gusset plate to the column, V sub C. We might also have a moment here. Same thing as at the beam side as well. We have a horizontal force, vertical force, and potentially a moment. And this must be completely in equilibrium. That's critical. We got to be thinking equilibrium as we're doing all these kinds of calculations. Now, we need some way to determine what these forces are. Looking back at this, we have 6 different potential forces on that gusset plate. So we need some way to pin down, at least some way to pin down a set of these to use in design. So we have a tremendous tool for this called the lower bound theorem. I think it was first articulated in detail in the way we use it in the 1950s. This is described in Design Guide 29 in Chapter 4. We note these corner connections are statically indeterminate. There's an infinite number of these force fields, we call them, just because it's quick, 2 syllables. A force field is just a combination of the HC, VC, MC, and so on, those 6 different forces, or 4 forces in 2 moments. There's an infinite number of these force fields that we can have. And we probably couldn't say which occurs at the ultimate strength to save our lives. There's just no way. For one thing, if you tested 5 of these in the lab, you would probably get a bit different results for all 5 tests. So there is no perfect correct answer. So there's an infinite number of these. We need some way to pin these down to get a design set of these forces. The cool thing is this third bullet point, the combination of these forces, the force field, that produces the highest ultimate strength that's closest to the true solution at the ultimate strength. That's going to give you the strongest one of those you can come up with. That's going to be the closest to correct. Now we do note, while we have lots of leeway in picking out these force fields, the choice of those forces is going to affect the economy of the connection. Shown graphically, this lower bound theorem looks like this. On the x-axis, we have all the different force fields that we could have, and this is obviously very schematic. On the y-axis, we have predictions of ultimate strength. And there's one unique point here that is the force field at the ultimate strength. That's just one unique point. If we pick some other force field, say this one, we pick this one, we can predict some ultimate strength of this equation. It's going to be less than the true. So we're either right or we're conservative. So this is fantastic because it gives us a way to proceed forward with our designs. Note this is the opposite of the kinematic method with the virtual work that we use for end plates that we talked about a couple of weeks ago. That does the inverse. You're assuming a collapse mechanism and you're backing out the ultimate force from that. And that one you're either unconservative or right. So you end up doing lots of calculus there trying to minimize solutions. Here, not so. We can pick a force field and move forward with it. Now, we can't just pick whatever we want, though. There are some requirements. The requirements of the lower bound theorem are, first, the force field must be statically admissible. Everything in this problem must be in equilibrium. The gusset plate, just zooming in on it, The sum of the forces in the horizontal direction and vertical direction for the gusset plate must both be equal to 0. The sum of the moments must also be equal to 0. We can get these pretty darn close to there. We might have some round off, but we're going to get those down pretty darn close. Second, no limit state can be exceeded. It must be safe. So we've proved this by R sub u can't exceed PRN for any of the limit states in the connection. So what we're looking for here is a statically admissible and safe force field, or combination of these 6 forces on the gusset plate. Note that we need some ductility in our connection for this to work, because if one part of the connection starts to receive a little more load and it starts to be overstressed, it can't just break like glass. It has to hang in there. It has to support its load and hang in there while further load redistributes to other parts of the connection. So in summary, though, we're looking for a statically admissible and safe force field. Now, there are various options for this. In Design Guide 29, they show a kind of a funny one called the KISS method, keep it simple, stupid method. And with this method, what you do is you just zero out the horizontal force at the column and the vertical force at the beam. Just choose the force field that has those two zeroed out. Now, to have equilibrium now, though, you've got to have this moment at the beam and or moment at the column. This still must be in equilibrium. This is especially useful if, for example, say you have a light HSS column and it just can't take anything horizontally here, you might just choose to set that to 0 and move on, for example. Now, you won't get the most economical connections using this method typically, though. And there's a couple other methods in there. The method that we typically prefer is called the uniform force method, and it's shown in detail in Design Guide 29 and in the manual, Chapter 13. The cool thing about this method, or one of the cool things, is it eliminates the moments on the gusset plate. You have no moment at the column connection or at the beam connection. This method complies with the lower bound theorem. It's been shown to produce safe and economical designs, so therefore it is emphasized, not only I guess recommended, but at least emphasized in Design Guide 29 and in the manual, Chapter 13. The basic idea is we have these control points, the center of the column and top of the beam, center of the beam, face of the column, and this control point over here. And the resultants of these forces are going through these points, so we can get rid of the moments and still have some of the moments equal to 0, because all these forces are going through the same point. That's the basic idea. So blowing it up, you see it like this. We have the brace force goes through this point 0. This work point is at the center line of the column and the beam. At the column connection, the resultant goes through 0 also, and the beam connection, the resultant also goes through this point 0. So no moment required here or over here to have equilibrium. We need to run down a few things here. First, what's this E sub B that you see right there? That's the beam depth over 2. E sub C is the column depth over 2. And we have these two dimensions, alpha and beta, and we're mainly going to be working with those. Alpha is the dimension from the face of the column over to the center of this connection at the beam side. Beta is the other way around. Beta is from the top of the beam to the center of this connection up here. Now, we can't just pick whatever we want for those. We need to set those to have specific proportions. And there's a snazzy equation in the manual, equation 13-1, that sets these for us really, really, really easily and awesome. Look at this equation. If you satisfy this equation, then this is all set up correctly and you have no gusset moments. And your gusset plate will be in equilibrium. It's alpha minus beta tangent theta, and theta is this angle right here, equals E sub B tangent theta minus E sub C. So in practical terms, what we're going to do is we know E sub C and E sub B. We know theta. somehow or another, we're going to pick alpha or beta depending on some practical constraint or whatever. It doesn't matter. You pick one of them and you calculate the other one to satisfy this equation, and then you're good. You're in this method then. So it's very, very, very convenient. Just a very quick look at the derivation. The complete derivation is in Design Guide 29, one of the appendices, forgot which. You can take the gusset plate, some forces in the x direction, and you get this equation, 1. Some of the forces in the vertical direction, you get this equation, number 2. Just simple equations. You combine these two, use some angle relations, and what you get from that is very, very, very simple. You get this. You get this parameter R, which is just the distance from the work point to this intersection. You don't care about that so much. You just need this number. And given these 4 parameters, you can calculate this in inches. And then VC, HC, HB, and V sub E, all 4 of these forces are calculated using these equations, and you really can't get simpler equations than those. So once we have alpha and beta set up, we can get these almost trivially. Let's talk a little about the beam-to-column connection, because there's a lot going on here. First, let's trace the forces from this column connection of the gusset. We have VC and HC. HC comes around through shear in the column down to here. So we have a pretty good sized shear in this column right there. The interface force, as far as left-right forces go, we have the transfer force and HC adding together or subtracting depending on their signs. So you have this force right here. And you can see it better over here. It's A sub B plus or minus HC. This can be a large force. Note also that the engineer record needs to give us this. The engineer record can't just give us the brace force and say go. It has to give us much more than that. It's got to give us A sub B. And by the way, R sub B also need this one too. Now, tracing the forces from the other direction, we have the forces coming down from the gusset on the beam. The big highlight here is that this V sub B can be 200 or 300 kips pretty quickly. And you add that to R sub B, this can be going down. It doesn't have to be going up. This can be going down, adding to R sub B, and you can have a pretty good sized force here. First thing is, it seems like when you're designing connections as the connection designer, the engineer record will throw a W8 in here, and you can imagine the chaos. Last job I worked on actually had that. 8x21s for the brace frame beams. So throw a pretty generous beam in there. That'd be nice, because we can have 200 or 300 kips here. Also, of course, this shear connection is going to get hammered too. One other thing, as far as communications go, if this is an HSS column, we really need to know this so that we can calculate. We need to know the axial load so we can calculate the Q sub F factor. One more thing, and this is from a job I've seen over just the last couple of weeks. This connection of the beam to the column could look like a shear tab. It could be what's called a shear plate or web plate there, and you got to watch out on the shop drawings, because I'm looking at a job right now where the detailers threw in horizontal short slots at all of those, and of course that's no good when you have this big axial force. And they have about 50 places where they're going to have to reinforce those connections now. So watch out for that. No horizontal slots. Limit states, let's talk about those now that we talked about the force distribution. First, going to this connection here. This is the easy part, obviously. We have these basic elements. We get the brace, the web plates, and the claw angles. We just have these basic limit states there that we've seen before. Now moving to the gusset plate. At the brace to gusset connection, like in this region, we have shear transfer. We have the Whitmore section. And on that Whitmore section, we can be checking check tensile yielding or tensile rupture if the brace is in tension, or compressive yielding or buckling if the brace is in compression. And we can have block shear as well. So let's talk a little about those individually. On the Whitmore section, we can have, this is what the Whitmore section would look like in this particular connection. You start at the end of just over the length of these bolts, spread at 30 degrees, and you have a section about like this. Note there's 2 bolt holes coming out for the tensile rupture check. And obviously, if the brace is in compression, you have compression in this region instead. We also have block shear along this U-shaped pattern like you see in this picture right here. Now moving to the gusset plate to beam connection. These are typically going to be fillet welds. Yes, you could have CJP welds, but we got a lot of length there, so hopefully we can get away with fillet welds. One oddity here is even though we're saying there's no moment there, we're going to increase the fillet weld requirement by 25% for non-uniformity in the distribution of forces along there. There's several things playing into that. Part is there probably is a moment there. Second is this beam could be bending a little there. So we have some non-uniformity. For a lot more information, go see the paper by Chris Hewitt and Bill Thornton. We can have beam web local yielding in this region, and that doesn't matter if the brace is in tension or compression. If the brace is in compression, we can have web local yielding or web local crippling in this region. If this beam is an HSS, then the vertical force in this gusset plate can cause a punching shear and bending. And you see in the manual, this location here is where you find the checks for those. Now, let's go to the gusset plate to column connection over here. Now, this could be an end plate, double angles like you see here, or it can be a plate that looks kind of like a shear tab. It's just a plate there. If we have angles or an end plate, we have prying forces due to the bending of the angle or end plate or the column. We have column web local yielding in this region, column web local crippling in this region if the brace force is in compression. Again, if this is an HSS column, we have punching shear and wall bending. I'm moving to the beam to column connection up here at the top. First, we have beam shear yielding, and as the connection designer, you don't get to pick that beam probably, so you might want to check that early. Maybe you can get an RFI out or something to get a better beam if that's a problem. Again, normally we don't care much about shear, but here this shear can be large. We can have angles, end plate, or a web plate there for this connection. If it's angles or an end plate, we have prying forces, as we described a couple of times. If it's this web plate, we got to watch out. The detailer will throw horizontal slots in there just because he's putting those everywhere else on the job for every other plate that looks like that. We have column web local yielding in this region. If this beam is putting a compressive load in here, then we have column web local crippling. Watch out, because we can also have web compression buckling because we have this opposing force on the other side. If we have compression coming from both sides, we have to check web compression buckling. Again, if we have an HSS column, we need to check punching shear and wall bending. And start checking those early because they're probably going to cause some trouble. Now, let's do a little example. We have this bracing connection you see on the right in a brace from a brace spring, W21 by 83 beam, double angle 8 by 6 by 1 brace with 840 kips at 47.17 degrees, W14 by 99 column. We have a 100 kip force transferring in from the adjacent bay. Now, tremendous amount of work to really deal with this connection. What I want to do is just first get the forces pinned down, a force field pinned down by the uniform force method. Select some plate dimensions, evaluate some of the more interesting and least obvious limit states. Note we have an end plate here on the end of the beam and gusset. So this is what we have. So let's dig right in and start working on this. Our materials, you can see we have 7/8 inch 8490X bolts, standard holes, 8992 beam and column, 70 KSI welds, and the plate is grade 50. Now, first step, let's determine some gusset plate forces using the uniform force method. Here are our governing equations, and here's our generic situation. We need to know E sub C and E sub B. That's just half the beam and column depth. E sub C is 7.1 inches. E sub B is 10.7 inches. We need the vertical component and horizontal component of the bracing force, and here they are. Just the vertical component is 571 kips, and the horizontal component is 616 kips. Now, here we have a decision point. We need to pick out an alpha and a beta. For the alpha, I just want to take this approach. It's not the only one. We could do something else. But I'm going to pick out an alpha and set beta. To pick out alpha, this is not the way to do it. It's just one way to do it. You pick it out whatever makes sense for your problem at hand. In this case, I'm just going to assume we have 7/16 inch fillet welds, but double-sided. I'm going to pick out a length of weld that's required to resist this 616 kips. Using our shortcut equation, we need 31.6 inches along here. So I'm going to try an alpha of 17.5. Now I'm just setting that. There's no magic there. You can use something else if you want. Now, but beta, I can't just pick something. I got to set that based on this equation. I know everything else in this equation but beta. Back out beta 12.1 inches. So I'm going to set this at 12 1/8. And that's 7 rows of bolts, like you see there. The first row is 3 1/8 off the top of the beam. So I've set beta. Unfortunately, if you start rounding that off very much, you won't have things will be pretty close to in equilibrium, but not quite. So you need, I guess, how fine you cut that depends on your preference. Let's compute these interface forces. We have our R, that we have all these right now, so we can just go ahead and calculate R, 33.5 inches, and calculate our forces HC, VC, HB, V sub B, just from these very simple equations that all appear in part 13 of the manual. Notice these are pretty big. They're not enormous, but they're pretty big. So our internal force distribution looks like this. Start at the gusset plate. Here's the applied load from the brace. These 4 forces here are the ones we just computed. And this gusset plate is in equilibrium. You can verify that on your own. This 178 carries across to the column as shown there. 303 also carries across to the column. Note this 178 is equilibrated by 178 here, so there's 178 kips of shear in this column in this region. Going to the beam side, we have this 268 carrying across, and that 268, if this brace is in compression, that's adding to this 50. So we have a pretty good size shear there. The 50 is just a reaction at the end of the beam just due to other loads. You can see how all these are adding up. We have the 100 kip transfer force adding with this 178. So the interface force right here is 278 kips as far as the compressive force goes. Note if this force was in the other direction, these would all be reversed. So let's take a few of these limits so you can check them, just sample ones. The gusset to beam weld, you can see the required force for that is the resultant of these 2 forces, or 513 kips. We need to know the angle that resultant makes with the horizontal. That's 31.5 degrees. From that, we can calculate our number of sixteenths that are required, and it's 4.63 sixteenths. Now, for this particular weld only, we increase it by 25% for the non-uniformity of the forces. So increase that, 5.78. So we're going to use, or we're going to say to use, a 3/8 inch double-sided fillet weld all along that interface there. Now let's go to check the plate strength down there. For these checks, we have tension and compression. The tension is this 268. Tension is shear. The tension is 268. The shear is 438. design tensile yielding strength from section J4 of the spec is 1510 kips. Greatly exceeds TCBU, so it's okay. Same with the shear yield strength from section J4 is 1,010 kips, and that exceeds the 438 kips, and it's okay. Notice there's a tension and shear interaction equation in part 9. If you're pushing both of those at the same time, you should probably go check it also near the first of part 9 of the manual. Usually doesn't matter much, and certainly wouldn't matter here. Now, going to beam web local yielding, we have this vertical force. So we need to check web local yielding along the critical section along this line. So we pull the properties from table 1-1 of the manual. Now, going into our equation, pick the one that applies when the load is at the end of the member. Plug all of our numbers in, you get 949 kips that exceeds the 268 kips, so it's okay. Now let's move to the gusset to end plate weld. We hit this real quick because it's pretty similar to our other weld. We have the resultant force of these two. That's the required strength. We have the angle. Go through our shortcut equation, and we need 4.45 sixteenths of weld. We know that a min is a quarter inch from the table J3 or 2.3. So I'm going to round this up to 5/16 and say use 5/16 inch double-sided fillet welds. Now let's move to probably the most exciting calculations in this part of the seminar, our session. We need to check the end plate to column connection. These forces getting across this connection. There's a lot going on here. We have our W14/99 column, and here's some properties. The gauge on these bolts is 5 inches in and out of this picture. We have 14 7/8 inch grade A 490X bolts. So we can look up in the manual tables 7-1 and 7-2 the individual strengths of those bolts. The design strength for one of these bolts in shear is 37.9 kips. The design strength for one of these bolts in tension is 51.0 kips. Now, if we have no prying action, then the force in one bolt is just simply take the applied force and divide it by 14. So for shear, it'd be 21.6 kips. For tension, it'd be 12.7 kips. Now, just as a preliminary check, I want to compare these to these two design strengths. And you see that they're both less than. So it's okay so far. We need to verify we don't have any prying action, and we also need to check these bolts for combined shear and tension. So let's first look at the prying action. We've assumed no prying action. So we need to go into manual part 9 and verify that. We have a 3/4 inch end plate, and this picture you see is a plan section. This is the end plate, and this is the gusset plate going off to the right. And you see the gauge of 5 inches this way. We have 7/8 inch bolts. Now, in part 9, we need to track down some dimensions. First, this B dimension. This B dimension is from the center of the bolt to the face of the gusset plate. In our case, that's 2 inches. We also need B primed. B primed is the dimension from the face of the gusset plate to the edge of the bolt. That's where we're assuming, or in the design model, that's where this force is, in the bolt. That's B primed, and that's 1.56 inches in our case. Just take B minus a half of the bolt diameter. So we have those almost there on this limit state. When we look, this picture is an elevation view of the end plate. You can see the gusset plate in section. Here's the top of the beam. We need to know how high of a piece of this plate is the critical section that goes with each bolt row. And that's this dimension P that you see in part 9 of the manual. Now that's going to be the minimum of the spacing, or 1.75 times B below and above, so 2 of those. So the 3 inches controls. And we go to this equation in part 9 of the manual. Now, what this represents, T sub NP, we talked about this in session 2, is this is the thickness. That's the minimum to prevent prying action. If our end plate is this thick or thicker, then there won't be any prying action. All right, so we have all these parameters, so we can go plug these in. The only weird things, I guess, would be the phi is just reminding us this is a bending of the plate type limit state, so phi is 0.9, and we use F sub u, not F sub y. So 65, there's 65 KSI going in here. This is 0.672 inches. Our end plate is thicker than that. So that means there's no prying action due to bending of the end plate. Now we're not finished though, we got to check the column too. At the column flange, run through the same calculations, it's okay also. The end plate's thick enough and the column flange is thick enough, so there is no prying action. So our assumptions are okay so far. Now, now that we know there's no prying action, we know this is correct. The required shear strength per bolt is just a 303 divided by 14, or this number, or similarly for the tension. Here, this is the one, we know that there's no prying forces, so this is true. This one's true either way. Go into table J3.2 to pull out F sub NV and F sub NT. Now let's check shear. Our shear stress is the 21.6 kips divided by the bolt area, 35.9 KSI. We compare that to phi F NV, so the shear part of this check is okay. Now moving to the tension in the presence of shear, using our interaction equation again, just like we did before. Plugging the numbers in, we get 82.5 KSI. That can never exceed FNT, and it doesn't. Plug that into our equation, and we have 37.2 kips as the design strength for one of these bolts in tension in the presence of shear. That exceeds our required strength per bolt, so this is okay also. So both these are okay, so the bolts are okay for combined shear and tension. Let's check a column local or web local yielding. We have 178 kips. We use our equation that applies when the load is not near the end of the column. So we have 5 there, not 2.5. The only trick here is what do you use for the bearing length L sub B. And we're going to use from the center of the top bolt to the center of the bottom bolt for that. So we plug all these numbers in. We get 604 kips. That exceeds our 178 kips. So this limit state is okay. Now talk a little more about the beam to column connection. In this case, the beam to column connection down here. In this case, this is in compression. You see that we have 178 plus 100 there, and so this is in compression. So therefore, our limit states are going to be web local yielding, web local crippling, web compression buckling, because we have the opposing force. We have shear along there. It's really high, so we need to check beam shear yielding, beam to end plate, weld, and shear transfer. So let's check a couple of those. First, column web local yielding. The required strength, so we're checking web local yielding in this region over here. Our required force, or required strength, will be these two added together, 278. I guess the only trick here, again, is the same as before, is what do you use for the bearing length? And I'm conservatively just using the beam depth from the top of the beam to the bottom of the beam. If this plate was extended down a little bit, you might spread the load through that plate a little bit like you see in Design Guide 24, and also the other direction. I'm just conservatively not doing that. I'm just going to use the beam depth only. And from this, you see that going in here. We get 686 kips, so it's also okay by a wide margin. Column shear, we've got to watch out and not forget this. Shear is so easy to forget with steel because it doesn't matter so often. Here we have 178 kips of shear in this region. That's nothing to sneeze at. If you go to table 1-1, there's no V footnote on this section, so that means that G2.1A applies. So this is the strength, 207 kips. that exceeds our 178 kips, so it's okay. But you can see how it's not okay by a huge margin. Column web local crippling. Here we have, again, the required forces, these two added together, 278. This is not near the top of the column, so we pick equation J10-4, and this is our equation. Our design strength is 693 kips, exceeds the required strength, so web local crippling is okay. Here's a tricky one. We got to check web compression buckling because we have an opposing force. We have opposing compressive forces. Our equation for web compression buckling is equation J10-8 that you see here. The only interesting thing, I guess, for far as calculating this goes is, first off, what's H? Probably going to get that from the H over TW ratio that's tabulated. So the H is 11.4 in this case, and putting that in here. Now, Q sub F is 1 for W shapes. This is actually not okay. So we would need to add some stiffeners in here. Just a few notes in closing. We have not checked all the limit states. Go into Design Guide 29 for complete design examples that are just voluminous. I mean, those guys really did a lot of examples in there in tremendous detail. They illustrate all limit states to great detail. If this brace was compressive, a few things changed. So just in closing, let's just mention those briefly. First, the beam to column connection would be in tension. That means it would be like the gusset to column connection that we just looked at. Next, beam web local crippling would also apply. Finally, we would need to look at gusset plate flexural buckling, or just compression, and that could be compressive yielding or flexural buckling, and we have K of 0.5 in this case from Design Guide 29. So we have compression, yielding, or buckling in this region. K would be 0.5. Now, in Design Guide 29, there are various other cases. Some of them have K of 1.2, so go in there and look and find a connection like yours to see what to use for K. With that, we're done. So thank you all so much for attending our sessions, our entire webinar series. And I want to say one last time to thank Dr. Thomas L. Murray for giving us these slides as a start, giving us his slides as a start for these slides that we have developed during this entire webinar. So that was a huge help. Also, thanks to AISC for having me here at all. So anyway, with that, I'll send it back to you, Nate, and guess that's it.
All right. Thank you, Brad. So I'm going to ask everybody to go ahead and turn your attention back to the slides window, and we'll do a couple of polling questions and then get to some questions that you all had for Dr. Davis. So you should now see the first polling question in that slides window. Again, focus on the slides window. And the first one is a true or false statement. And the question is as follows: true or false? If the uniform force method is used for a corner connection, the beam to column connection is unaffected by the brace force. Is that statement true or false? Giving everybody a chance here to get their answers in. Again, that true or false statement. If the uniform force method is used for corner connection, the beam to column connection is unaffected by the brace force. Is that true or false? All right, I'm going to go ahead and close the poll. All right, Brad. It looks like about 90% of the audience thought that was a false statement. Did they get that question right?
They are correct, because the vertical component But the vertical force going from the gusset plate into the beam has a huge effect on the beam end force. And also the H sub C, the horizontal component the horizontal force from the gusset to column connection, works its way around into that beam to column connection also. So those are huge. I mean, and what ends up happening is you'll have members on jobs that are undersized, and then when you start factoring those kinds of things in, the connection starts getting hammered, and it's really hard to see how to fix it then, because sometimes the beam will be too shallow, or the column will be an HSS with a thin wall or something like that. So then you start to have all kinds of trouble getting those to work. So be watching for that. It's not just a matter of seeing how many bolts you need in the brace to gusset connection. That's just the beginning. This is where the problems really can occur.
All right. Let's go to the next polling question. And you should see it on your slides window there. This one's multiple choice. How is the effect of combined tension and shear and bearing type connections addressed by the specification? Is that A, the nominal tensile stress is modified based on the level of shear stress in the bolt? Is it B, an interaction equation from Chapter H is used after the bolt has been checked for tension and shear independently? Is it C, a reduced nominal tensile stress is taken from table in section J3? Or is it D, a strength equation containing the angle between the line of action and the connection fang surface is used? Again, the question is, how is the effect of combined tension and shear in bearing type connections addressed by the specification? All right, so let's go ahead and see what the results are. I'm going to close the poll. All right, Brad, kind of have a interesting distribution of answers here. About 46% think that that answer is A, 33% think that that answer is B, and we have about 12% thinking it is D. What is the correct answer here?
It is A. This is our FNT primed that we saw a couple of times in the calculations. This is equation J3-3A in the specification. So the second one is almost, the part B is tempting, or option B is tempting, but we don't go to Chapter H. It's also, and so really it's A. A is the answer.
All right. So let's go ahead and do some questions. And the first one brings us to slide 15. And the question is, this question asker is wondering about a connection that might be a little bit more complicated, but similar to the one that is shown. So the question is what if this connection had 3 braces? So perhaps one that is like the one shown, one that is mirrored from the one shown in the lower right, and one that has a horizontal brace coming off of this gusset plate. What would be your approach to evaluate that type of connection? And do you have any general advice for approaching a connection like that?
Lots of engineering judgment. That kind of reminds me of a chevron type of connection, and those are covered in detail in the Design Guide 29. One of the things about chevron type connections is that they are not statically indeterminate like our connections we were just dealing with, our corner connections. So you're going to rely on lots of section cuts and free body diagrams to determine forces and loads there. And there's going to be lots of judgment. Like, for example, you have these three braces are coming in. The Whitmore sections may be overlapping between the three. It depends on which ones are in compression and tension, and with different load combinations, and so on. But no, I don't have just a prescriptive advice. Just lots of free body diagrams. Go look in Design Guide 29 and make sure you have the chevron stuff down pretty well. There could be moment on parts of it, so you have EMU versus FEMN checks, and you see those on the chevron type connections in the design guide as well. So, wish I had just a prescriptive answer, but lots of judgment, lots of free body diagrams.
All right, going to slide 18, and a couple questions here. One question is, I typically use K equals 1.5 to 2 for buckling length of gusset plates. Do you have any comment on those types of effective length factors for these gusset plates?
Well, there was an AISE journal paper from a few years ago. Don't remember who wrote it, but it was probably about 2005-ish. 2000 to 2005, and there were a few different examples in there. And I do remember one was similar to this, and in there they were using 1.2. And then there's also where the 0.5 came from for the gusset that's connected to the column and the beam at the corner connection. So they have 1.2 for some of these. For some connections that look about like these. Also in Design Guide 29, there are connections like, for example, if you have a corner connection that has the geometry of the brace is such that the gusset only connects to the beam, not to the beam and the column, and they're using 1.2. So you can obviously use a little higher than that. That's just going to be conservative or right. One or the other. You're not going to be unconservative, obviously. So yeah, I'd say just try to find that engineering journal paper and see what you think about that. And also Design Guide. It's a Bo Dowswell paper, actually. Effective length factors for gusset plate buckling. One of our colleagues is alerting me to here. So check that out.
Mm-hmm. Okay, another question, similar or related question on the effective length here, LC. For this, is the LC, would you use the clear distance from the end of the connection to the edge of the bolt hole? Or how would you recommend considering what L is for this?
I would go from the weld, or from the support over to the center of that last bolt hole on the left. Now, this gets more complicated when the brace is on an angle. And there are examples in Design Guide 29 showing how to work that out.
All right. And that you would use that for L, correct?
Yes, that's L, not KL.
Yeah.
Not LC, that's just L.
Okay. All right. I'm going to go to, well, first go back a slide. And so you talked about using the Whitmore section concept to establish a weld effective length on this slide, and then you went and applied that to an example problem that had a welded connection between the gusset and the support. And this question asker is asking about a connection like this on slide 27, where you have bolts rather than welds. And so the question is, would you apply the Whitmore section to the bolted connection in tension? Would you be, in certain situations, only considering bolts that fall within that Whitmore spread?
That's a really good question. I've never seen that done before. I would say typically I probably wouldn't, but I could imagine a case where there's a a whole bunch of bolts up and down this for whatever weird reason. And then the Whitmore section, you could use some engineering judgment and decide to discount some of those bolts. I've never seen that done before, so that's actually a pretty neat question. But I guess I don't know. I guess tentatively I'll say probably not, but hey, who knows, maybe.
All right. Let's move to slide 45. And on this slide, you commented not to use slotted holes in the beam-to-column connection. And somebody asked, would you find it acceptable to use slotted holes for that connection if you were to use a slip-critical connection?
Yes, but you probably never get it to work. The forces are pretty high there, and as we saw earlier, we only for the one bolt we were looking at a minute ago, it was only 9-point-something kips per bolt. So it's going to be tough to get that to work. I think the key element here is communication between the EOR and the fabricator detailer, because the detailer, the problem comes when the detailer doesn't have any idea there's any axial in that connection. So to them it looks just like a standard. It looks just like a single plate shear connection. They throw a 3/8-inch plate in there with their 1-inch wide by 13/16 tall slots in there, and they just go. And there's the problem. So this is mainly a communications question. There's a lot of deficiencies in communicating the forces between EORs and the fabricator when it comes to bracing connections. I mean, very often you just get the brace axial load and that's it. And as you can see from the calculations in here, there's a whole bunch of other forces that are needed.
All right. A general question. I'm not going to go to a specific slide for this one, but the question is, in general, do you find it acceptable to attach a brace with just one bolt? And if so, how would one consider shear lag factor to be calculated when you have essentially a connection length of 0 because you only have one bolt?
I think I just wouldn't do that. I guess if you had just the absolutely completely trivial connection, I guess maybe it doesn't matter much there. But anything other than that, I'm just probably not going to do that. And if I needed to do that and then establish the strength, I'm trying to think how would one even go about doing that. I guess you have block shear there. That's going to be very, very weak if you only have one bolt because it's only right there. The shear, the A sub N V, the net area subject to shear is going to be really small. So I guess I would, in general, discourage even doing that at all. But I know how this works. That's just happening, and then the person asking the question probably can't do anything about it. Hopefully this is only in a totally trivial kind of situation.
All right. Let's go to slide 48. And somebody asked, in a situation like this where you have the Whitmore section encroaching on the adjacent beam there, do you think it would be acceptable to just maybe neglect that length of that Whitmore section that gets into that beam?
What I would do with that is just pretend like the plate goes on up there, because there's two options in my mind about what to do with that. First would be either pretend like the plate goes all the way up there, although we know there's beam there, because the beam that's going to be in the region with the fillet, so there's a lot of steel there. So I think it's conservative just to use the gusset. You got to use some judgment. There could be some weird case where that's not conservative, but I'm typically going to just pretend like the plate goes on up there. I think I've seen in the past an example where the example developer had used some of the beam strength up there instead of plate strength up there. And I guess one could do that sometimes as well, but I'm probably just going to pretend like the plate goes on up there. Now, if it goes up in there, if that whip goes way up into the beam, then I might stop. I might balk at that a little bit, because now it's a lot different. But that doesn't usually happen. I know one of the popular connection design programs, if that happens right there, it just stops and says like this doesn't work. Just forget it. Like, nope. But anyway, I'll stop with that. All
right. And I think we'll have to stop our question and answer session with that as well. Unfortunately, sort of have run out of time, but thank you to everyone for those questions. And we have received all the questions that were submitted, not just the ones we got to, so we will work with Brad and respond to those question askers via email if we did not get to those questions.